Okay, so other than chapter 12, right, what we'll do now for a few weeks is information that can seem quite abstract. It's not something that I have the equipment and the resources to show you, right? So and even if we had some equipment, we wouldn't have equipment to look at everything we are going to talk about. So you have to take a little bit of a leap of faith and trust the science for a few weeks, all right? Because it's not something you can see, okay? Now, that for some people can be a little frustrating, overwhelming, difficult to get their head around, okay? I try to make it as easy as possible. This is not biology. I am not Dr. Barlow. So those of you that are taking class with Dr. Barlow may or may not have already covered some of this information. If you've already done it, you're going to go, oh my God, this is so much easier. If you haven't done it, when he does it with you, you'll be sitting there going, oh God, this is way more difficult, right? Because I make it as simple as possible. Our class is about application. From my perspective up here, you all at some level are going to be teachers, right? Coaches, therapists, actual PE teachers, personal trainers. That's all version of teaching. So my job, bless you, is to make this as applied as possible so that you understand how to use it when you're teaching. Right? Slightly different for Dr. Barlow. That's not his job. Right? He's not working with you as a teacher. Okay? So, having said that, we will get to a point in the semester where everything we do now becomes very applied. We'll look at training programs, we'll look at how to get stronger, we'll look at nutrition, okay? But we start with the nitty-gritty, with the small stuff, with the science, with the chemistry and the physics first, all right? So yell at me if I'm going too fast, okay? My dad and I were talking about this at Christmas, and he said, well, why don't you flip it around and do it the other way? Do the applied stuff first and then give them the science. Like, that doesn't make any sense to me, right? So, and I'm organising the class, so unfortunately you get stuck with my version, not my dad's version. But to me it doesn't make sense to tell you how the body adapts in response to exercise when I didn't teach you what was going on in the body in the first place. All right? Okay, so, oops, come back to one. There we go. Remember to run down these learning objectives versus the set that is in the beginning of the chapter, just in case I've cut anything out there. All right? And we're going to start looking at energy production. Why do we need energy, right? So as a human, we need energy for basically everything, all right? Even just to sit still or lie still. So remember that idea of basal metabolic rate or resting metabolic rate. How many calories do I need to do absolutely nothing except survive, right? Everything that goes on in our body uses energy. We're specifically interested in energy with regards to movement, right? So that's where we're going to concentrate our ideas. So making energy from the food that we eat is called metabolism or bioenergetics. Two fancy terms, doesn't matter which one you use, but you want to recognize both of them because depending on which resource you look at, it'll get called one or the other. All right? Hopefully you remember from school that all the energy we have ultimately comes from the sun, right? The plants use energy to create carbohydrates. Mammals and humans and cows and everything else eats the plants to create muscle. We eat the cow, right? So everything ultimately comes from the sun and plants. So we need to take slightly better care of the plants. We've got half the planet on fire at the moment, I think. So we're not doing a very good job right now of taking care of things. When we look at our nutrition, then we have three main energy sources, all right? Although, as we'll discuss, one of them we don't really use for energy. Okay, our first is carbohydrate. So carbohydrates are brilliant, okay? They're relatively small molecules, so it's very easy to break them down and get at the stored energy within the carbohydrate. All right, so that makes them a ready source of energy. It's why if you're lagging a little bit during training or a competition, a bite of banana or a handful of raisins is a really good choice, and you get a quick buzz from that because that's carbohydrate, right? And it's very easy to get at that energy that is stored in that banana. Okay? We have three forms, so monosaccharides are the simplest, and the absolute simplest of those is glucose. Fructose is fruit sugar. Galactose is a combination, I think, of fructose and glucose. Out of my depth there. That's more chemistry than I know. Disaccharides, so the kind of sugar that you have on table or that people put into their coffee and that's sucrose. And then we have our polysaccharides, which are important because our polysaccharides have the starches, so potatoes, rice, pasta, those kinds of carbohydrates would come under here. And they also have a cellulose group. Cellulose is a form of carbohydrate we can't break down. Humans can't break down. Cows do, right? Humans can't break, I think rumination is breaking down cellulose. I haven't done any cow biology. Right, so cellulose for humans is a form of carbohydrate we cannot break down. That means it passes through the digestive tract as a whole unit. That's really important for digestive health, for the health of your colon, right? So we don't want to cut out cellulose because that's part of the thing that keeps, it's not going to keep my muscles healthy, it's not going to help me move, but it's going to keep my digestive system healthy. Okay. And then two fancy words, glycogenesis. Genesis is the beginning, right? Glycogenesis means the beginning of glycogen from glucose. So I take glucose molecules, I create glycogen, and glycogen is the storage form of carbohydrate in humans. Right? We store it in muscle tissue and we store it in the liver. Glycogenolysis, which I'm probably not saying right, is breaking down the glycogen back into glucose. So that occurs specifically, it occurs in the muscle, but a more important version of this occurring for us to think about is when we need to break down stored glycogen in the liver, turn it into glucose and dump it into the bloodstream, carry it around to a muscle that needs more energy available. All right? So we'll come back to that idea during the semester. Okay, so this is what a glucose molecule chemically looks like, all right? I do not care. Don't care. I'm not putting that there because you have to know this, okay? I'm putting it here because for some of you, knowing this will help you. For others, it's like, okay, too many letters. However, what we do need to pay attention to is that in a carbohydrate, we have carbons, right? 6 carbons. And that 6 carbons is important in a week or so. Okay? So glucose, as I said, is the most simple form of sugar. It's a monosaccharide. It is carried around in the bloodstream, so it's often called blood sugar. But we're really talking about carbohydrate and glucose. Okay? And that can be used directly for energy from the bloodstream, or it can be transported into the muscle tissue or the liver and turned into glycogen for storage. All right? We already did that bit. So this is glycogen, and each of these little molecules is a glucose. So glycogen is just a great big lump of glucose all stuck together. Okay. The liver glycogen, as I said, is used to restore levels of carbohydrate in the bloodstream. And the muscle glycogen can be broken down and used directly within the muscle tissue for energy. So energy source number 2 is fats, all right? And again, this is just here for an example, not because you need to know it. But visually, right, what's important is look how many carbons we have here versus a carbohydrate, right? So fats are a very, very important source of energy. The problem with fats is that a fat molecule is huge. So it takes time to break a fat molecule down to get at the stored energy. So if the fire alarm goes off right now and we all have to get up and walk out of the building, you don't use fat to do that, because you can't break a fat molecule down that quickly to provide energy for your muscles to stand up and walk out of the building, right? So we would have to use either energy that's already in the muscle tissue or carbohydrate to do that, right? But fat becomes very, very useful when we've had enough time moving that we can access a fat molecule because it's got all this energy available. Okay? So from our perspective, what we want to know about fat, the pieces of the fat molecule, let's put it that way, all right? So we have fatty acids, and they're important because they're the piece of the fat molecule that is carried around in the bloodstream, okay? And fatty acids are usually an even number of carbon atoms, and then they can be labeled as saturated, monounsaturated, or polyunsaturated. Okay. From a health perspective, mono and polyunsaturated fats are considered more beneficial. People who have diets that are higher in those types of fats tend to have lower blood cholesterol levels, lower blood pressures, and things like that. Not that we're not going to eat any saturated fat, but the health literature would suggest that we try to limit that saturated fat. Okay. Triglyceride is the equivalent of glycogen for fats. Triglyceride is the storage form. Triglycerides are stored predominantly in fat cells, but also in the muscle tissue. Right? So if you go to the butcher's and you buy a nice steak to put on the grill, right? It's all very well to get the steak that is 98% fat-free, but it's gonna go hard on the grill and taste like a bit of old cardboard, right? What I want is a nice marbled steak that's got lots of fat running through it so that when I cook it, it doesn't dry out and it's got all that extra flavor to it, right? So, again, like I said, we don't cut out the saturated fat, we just try to cut down on it a little bit, all right? So if we think about fat as an energy form for humans, we have a limitless supply of fat. Even someone who is very, very lean has good fat stores, right? So unlike carbohydrate, which has a finite amount of storage room, so I can store my carbs in my muscles and my liver, but it's kind of like a big wardrobe, right? Once all my muscles are filled up and my liver is filled up, then any extra carbohydrate doesn't have anywhere to go, right? The stores are full. But the stores get used up very quickly, so I have to keep filling them up again. With fat, it's got so much energy, right, that a little bit of body fat provides huge amounts of energy. So I've got this limitless supply. So I can't deplete fat stores, and running out of fat isn't an option when we're looking at fatigue, right? Running out of carbohydrate can be an option, but not running out of fat. Make sense? Questions? Okay, so this is just a comparison to try to give you an idea of the difference in energy storage that we're looking at between these two sources. Okay, so for this individual, okay, and this individual is 143 pounds and 12% body fat. So 12% is right on the minimum for a female. So this could be a very, very lean female, or it could be a male, right? Anyway, 12% either way is someone who's quite thin, lean, okay? Bear that in mind. 110 grams, so that's about 450 calories of carbohydrates stored as glycogen in the liver. About 2,000 or so stored as glycogen in the muscle, and around 50 to 60 calories is floating around in your bloodstream like as glucose, as blood sugar. Right? So I've got somewhere in the region of 25 to 2,600 calories worth of carbohydrate in my body stored. Right? That's not a lot, really. Okay? When we look at the fat storage, if I look at subcutaneous and visceral, so think back to last week, remember visceral is the type of fat that is laid down around the organs in the trunk, and subcutaneous is the type that's under the skin. Then this individual is looking at almost 73,500 calories of stored fat at 12% body fat. Right? So imagine how many calories you have stored if you're someone who's overweight, whose body fat is 32%. Right? That's why you can put them on more extreme calorie restrictions. Not that that's very beneficial mentally for them, but physically you can. Right? Then we said we have some fat stored in the muscle tissue, about 1,500 calories. So this is nearly 75,000, right, versus 2.5. Okay. So we have to have carbs because they're small, the energy is readily available, very quick to break down and get at that energy bond. But fats are a great source of energy, it just takes a while to get at that energy. Right? I can't just access it very quickly. Question? Source 3. Okay, source 3 is protein. Proteins can be found in animals or plants. And actually, right now, they found 2 more amino acids, so most resources that you look up say that we now have 22 amino acids that compose proteins. And proteins' role in the body is to act as a building block. Right? Everything we make, when we do our exercise and we train, we make little micro tears in the muscle. We have to fix that, mend it so that we can carry on training. Right? If a child is growing, they need protein in order to build extra muscles and extra cells and extra hormones. Right? Proteins are divided into 2 groups. The first group is essential amino acids, and they're essential because we're not able to synthesize them within our body. We can't make them for ourselves, so we have to eat them for them to be available as a building block. Okay? The non-essential amino acids are non-essential because if we don't eat them, we do have the capability to synthesize them internally. Right? One of the things we have to pay attention to, and it's really relevant, right now there's a big push for vegetarianism and veganism, right? Which is fine, but it's a little challenging for an athlete because there aren't a lot of plant sources that are complete proteins. Soy is one. That's the only one that I know of for definite, right? So there's only so much tofu you can eat in a day, right? So the challenge for a vegetarian or a vegan eater is that they have to find a way of getting all these essential amino acids in their diet, but not from animal sources, right? So they have to combine beans and nuts, or chickpeas and something, right? They can't just eat chickpeas, because whilst they're a good source of protein, they're not a complete source of protein. So it doesn't provide all the amino acids. And one of the issues with that is if your body is trying to build a particular structure, right? So say we're building a house, and we've got all the tiles for the roof, and we've got all the bricks for the house, and we have the front door and the back door, but the windows are missing. Then the house isn't complete, right? I can't build the house without the windows. I mean, I can, but I wouldn't want to live in it without the windows, right? So it's the same thing in the body. If your body is trying to build a particular cell or molecule and it's missing one of the amino acids it needs, then it can't do the job properly. Right? Now, contra to the current trend in protein diets, where everyone will tell you what a great source of energy protein is, not for humans, right? It can be broken down, and we can use protein and access the energy bonds in protein for muscle movement. We don't, right? We use proteins as building blocks and mending fences and all this other work that they do, right? So if you run a marathon is what, 26 point, how many miles? 26.2? 26.2 miles, right? And you're not world class and running it in 2 hours and 3 seconds, or whatever the current world record is, right? The rest of us run a marathon, and it takes us 3 hours, 3.5 hours, 4 hours, 5 hours, right? Of that 4 hours, only 5%-ish, only about 5% of the energy that you need to run that marathon comes from protein, right? 95% of your energy to run a marathon comes from carbohydrate and fat. So if you go down to the max pack and you work your butt off for 1.5 hours, you do not use protein, right? You use protein afterwards to mend all the damage you did in the 1.5 hours, but you don't use protein as an energy source. And I'm emphasizing this because, as I said, right now there is this big media load of twaddle going on that's trying to sell protein bars and protein shakes and keto diet and all this other junk, right? So you've got to start to be a little cynical about what you read, okay? Because there are a lot of very attractive people going on television or in magazines saying, oh, I did the keto diet and I have never felt this good in my life. Right? It's probably not the protein in the keto diet that's making them feel that good. It's the fact that on the keto diet you also have to eat a lot of vegetables and fruits, and maybe they didn't do that before. Right? So just start. You might not agree with me yet, hopefully you will by the end of the semester, okay? The whole protein thing, not a good plan. Not a good plan. Okay, so the next little kind of, not molecule, well it is a molecule but it's a bit bigger, then is that we have to understand when it comes to energy production is how enzymes work for us, all right? Enzymes are made of protein, so this is an immediate example of why we need all our essential amino acids, all right? And enzymes are responsible for helping along a chemical reaction. So when I break down a lump of food, whatever type of food it is, that's a chemical reaction, right? So in order to help that chemical reaction, we have thousands of different types of enzymes, right? So enzymes work in what we call a lock and key configuration. So an enzyme, every enzyme has its own particular shape, and every receptor for that enzyme has a matching shape. And that means that only that particular enzyme can attach in that spot. Right? The way they facilitate the chemical reaction is that by jumping in and helping out means I don't need so much energy to make the chemical reaction occur, right? So they're not responsible for the chemical reaction, but they help it be more efficient and to work more quickly. Okay. They can work in catabolic reactions. So catabolic means breaking down. So I'm breaking down carbohydrates or I'm breaking down triglycerides to find the energy bond. Or they can work and help out in anabolic reactions where I am building, I'm making something from something else. So in particular, muscle tissue. Right? And when we start to look at the energy systems, we'll talk, particularly in glycolysis, we'll talk about rate-limiting enzymes, because sometimes there's a particular enzyme in the system that is crucial to the system working, and if that enzyme is missing because there's a protein, an amino acid missing, then the system can't work effectively.
Is glycogenesis and glycolysis the same thing?
Not glycogenesis, it would be glycogenolysis. It would be the first step of glycolysis. Yeah. So, enzymes are odd little things, right? They're very, very picky about their environment. So they have a particular temperature they like to work at, and they have a particular pH they like to work at. And when we mess around with the temperature and the pH, like we do in exercise, they don't like that very much, all right? So sometimes they'll slow down because we've added too much acid into the environment, and they go, I'm done. I'm not working in this, right? Well, if they don't help out, then the whole chemical reaction slows down. Doesn't stop because they're not the cause of it, they just help it, right? But it slows down. And if energy production slows down, I start doing this. Right? Instead of going that way, I slow down. So if we increase the temperature ever so slightly, they like that. They like to be a little bit warmer, and they speed up. Right? So we see better energy production. If I increase the temperature a lot, they don't like that. And they slow down or stop. And energy production goes down. Same with pH. Right? I've got a little window I can play around with pH. But once it's starting to get too acidic, they slow down, okay? Where are we? Okay. So what are we making? We keep talking about energy. Right? We're making ATP. ATP stands for adenosine tri, here's my T, triphosphate. Right? So, in humans, ATP is the energy molecule. Right? It doesn't matter that there's energy stored in the food, I can't use that energy until I turn it into an ATP molecule, and then I can use it for muscle contraction. And we make ATP through anaerobic metabolism. We have two systems that are anaerobic. Anaerobic means I'm not using oxygen. Okay, the "an" on the front means not. And I can make ATP aerobically. So I am using oxygen to help me make ATP. Right, so the adenine and the ribose kind of get clumped together and called adenosine because for us, they're not relevant in energy production for muscle contraction. So we don't have to worry about remembering, unless it helps you, you don't have to remember adenine and ribose, right? That can just be adenosine. And the adenosine then has 3 inorganic phosphate molecules attached with energy bonds. We have another version of adenosine that only has 2 inorganic phosphate molecules, adenosine diphosphate, ADP. So when we're looking at this, we're going to be talking about ADP and ATP. Right? It's important to remember that it's ATP that is the energy molecule for us. Okay. When we break down ATP to release energy for muscle contraction, then we're left with an ADP, an inorganic phosphate, and we release a hydrogen ion. That's problematical because hydrogen is acidic. So when we're doing a lot of muscle contractions and we're breaking down all this ATP to contract our muscles, we're releasing hydrogen, which, if it turns the environment acidic, slows down the enzymes. And that slows down energy production, and that slows down me. You with me? Make sense? We'll stop there. We'll start this on Friday. We had at least 2 people that cannot make 1 o'clock. They have other lectures, so we will have to meet at 2. I need to get out of here very, very promptly after class on Friday because we have to drive to Albuquerque for our race on Saturday morning. And so if you have questions for me, we're going to do them at the front end of the class. If you've got questions that aren't to do with the content that you want to ask me, please come in and talk to me while I'm setting up the camera, because I won't be able to stay and chat after class. Okay? Please tell me that's